So VPROMPT is the Vanderbilt-Pittsburgh resource for organotypic models for predictive toxicology. There's a lot of jargon in that we'll unpack in due time. The institutions involved are, as it states in the name, Vanderbilt University and the University of Pittsburgh. And the projects that are included are 4 different organ-on-a-chip devices. One for mammary gland, one for early limb development, one for fetal membrane, one for liver, and then finally there's a systems engineering and analysis project that ties all of those together. This project's interesting for toxicology because organ-on-a-chip fall in an interesting intermediate level of complexity. We're building on the effort that EPA has undertaken with its ToxCast program, where they were taking thousands of chemicals, testing them against hundreds of different in vitro assays to figure out which chemicals impacted which proteins, receptors, enzymes, and which chemicals impacted particular types of cells grown in homotypic cultures, right, single cell type cultures. To try to get a little bit better in terms of predictivity, we need a more complicated model. But we don't want to go all the way to an organism, right? That's the other level of complexity that's already been done. So an organ-on-a-chip takes multiple cell types, grows them in the right 3D arrangement and with low overhead fluid volumes so they can chemically communicate to better mimic the in vivo environment of particular organs or developing organ systems. And the hope is that that is then better predictive of what would happen for actual human exposures. But in the end, we were going to combine the organ-on-a-chip information with all of the ToxCast information and use that in this new paradigm of how do we do predictive toxicology based on all of those sorts of assays. The organs on chips are simple enough, right? We know all the parts, we know how it was put together, that we can go back in and dissect exactly what the adverse outcome pathway was. What receptor was hit, how did that impact a particular cell type, how did that change the interaction between cells and lead to a failure of the organ-on-a-chip. There's important impacts of chemicals on early development. Mammary gland is a tissue that undergoes multiple phases of development, some in utero and then during puberty, and both of those windows of exposure are important. Limb malformations are common. Fetal membrane, when it's impacted by chemical exposure, has been shown to increase the probabilities of preterm birth. And then of course it's important to include liver, where xenobiotic chemicals, right, chemicals that are not natural in biology, are metabolized. So it's clearly important to connect the organs because the chemicals to which cells are exposed in vivo usually pass through the liver first, and they're metabolized there. And the specialized hardware for doing that is important because we don't want to be moving these microliter volumes of fluid around. The fluid handling itself is very labor intensive. We would lose some of the fluid in the process. It's not easy to move those amounts of fluid around carefully. And we want these to be amenable to doing higher throughput screening. There's tens of thousands of chemicals in widespread use. We need to screen through all of those eventually, and to do that we have to have automated systems that allow dosing schedules and perfusion and moving chemicals from liver to downstream organ all automatically. So the microclinical analyzer brings to the table the ability to see the earliest effects of a chemical on any particular organ. Right? The microclinical analyzer is placed downstream, and it has sensors on it that sense important metabolites in the fluid that's passed over the cells. We can see how much glucose the cells have taken out of the fluid, how much lactate they've secreted into it, if there have been changes in the pH or oxygen levels in the fluid. And there's a few other metabolites we're working on for the microclinical analyzer. So I think of the microclinical analyzer as our canary in the coal mine. It's our first indication that anything's gone wrong with the health of the cells in the device due to a particular chemical exposure. The IMMS is important, right? IMMS being ion mobility mass spectrometry, because it gives us the best detailed view of exactly what the mechanisms of action are, what pathways are being impacted by a particular chemical exposure. Cells communicate with one another via chemicals in the fluid, and so when they are perturbed from their normal state, they change what they secrete into the fluid. Current steps with the device are validation. We need to take all of these organ-on-a-chip devices, test them against a few chemicals that we know should have effects and a few that we know should not have effects, and make sure that we get the historical answers from animal models and from human exposures. Then the next steps are to take the organ-on-a-chip devices and really make them amenable to higher throughput screening so that we can go through thousands of chemicals and characterize for all of those what are their impacts on these different developmental outcomes.